continue the hands-on training for reinforced concrete core wall building. The performance, we will do the performance-based design. For performance-based design, there are many documents coming out. The very first one is the Los Angeles Tall Building Design LATBSDC criteria guideline, and then year 2010 document is coming. The latest one is that one year 2010 05 document, which is Tall Building Initiative for the guidelines for the performance-based design of tall buildings. This is the general guideline, and then they also released PR ADC 72.1. That one is the modeling, detailed modeling procedures and acceptance criteria for the performance-based design. Together with those documents, we use ASCE 4106 document, which is seismic rehabilitation of existing buildings. It is updated in supplement number 1. Some of the tables are updated, but this document can be used not only for existing building, we also use for new buildings. Now this document is going to be updated with 2013 version, but it is only in draft version. This is the overall design procedure for the performance-based design. Firstly, we do the preliminary design using the code-based design procedure, using the design level basis earthquake. And then we do the service level evaluation using a 43-year return period earthquake, and then we also check the collapse prevention performance level for 2,475 year return period earthquake. In the preliminary design, we have to check. First, we create the finite element model in E-depths or sub 2000, and then we check the overall response of the structural system. We have to select the structural system using core wall system or dual system or moment resisting frame system. So we have to decide the system first, and then we model that system, and then first check the overall response. That step is also an important step for the in the first stage. We have to check the mode shapes, natural periods, modal participating mass ratios, base shear, base moment, shear wall frame interaction, story drift, story displacement. These overall response we have to check carefully. If the overall response, like mode shapes, the first modes are not pure translation, the torsion is dominant in first mode, so we have to revise and modify the system in coordination with the architects. And also check the natural periods. If the natural periods are very long, we have to stiffen the structure. And also modal participating mass ratio. From that information, we can determine the higher modes are dominant or not. Then we have to check the base shear. Base shear coming from the seismic loading as well as the wind loading. And also we should check the weight of the building. Sometimes we might make mistakes in the model, so the base shear are not reasonable. Sometimes we put the weight density of the materials, and the building weight might be overestimated. For residential reinforced concrete building, normally when we check the building weight, it is about 1 to 1.5 ton per meter square. the weight per area is about 1 to 1.5 ton per meter square. So if you calculate the weight of the building and then divide it by the total floor area, it is coming out 4 ton meters per meter square. Something is wrong in the load assignment. We have to check carefully. So from the base shear results, we also when we check the seismic base shear for the tall buildings, according to the equivalent static procedure, the base shear will be approximately 4%, 5%. If the for the 4%, 5% is for seismic zone, a very high seismic zone. If the base shear is coming out very large, 10% in equivalent lateral load procedure, so something is wrong in our modeling. So we should check those things, whether it is reasonable or not. And also from that we can determine that base shear and base moment comparison, we can determine whether the wind load is controlling or not. Sometimes wind movement is controlled in tall buildings. Sometimes wind seismic base in terms of shear, seismic shear is controlled. If you use the dual system, we should check the shear wall and frame in the distribution. In the code, if we use the dual system, our backup frame should be designed for 25% of the total base shear, whether it attracts or not. Sometimes our shear walls are very stiff. In that case, only 10% of the base shear may go to the frame. But if you design according to the code, we have to design the frame to resist 25% of the base shear. So in the load combination, we have to increase the load for the frame, but that 10% of base shear attracted by the frame is not uniform throughout the height of the building. At the upper floor, the shear wall will take more force because of the shear wall and frame interaction behavior. The frame is behaving like deforming like a shear deformation, but shear wall is deforming as a cantilever column. This is the shear wall and frame interacting together. Because of the lateral load, shear wall is behaving like a cantilever column, but the frame is behaving like a shear deformation pattern. So at the base of the building, the shear wall is not rotating too much. The frame is swaying too much, so shear wall attracts more. But at the top of the building, the shear wall is moving more. The frame is not moving too much compared to the shear wall, so the frame attracts more forces. So if we have the shear wall and frame distribution, the frame is taking 10% at the base, but at the upper levels it will be more than 25%. So we have to check the shear wall frame distribution and create the load combinations to design the frame to resist 25% for the lower frames only. If the frames are attracting more than 25%, we do not need to magnify the forces. This is for code-based procedure. And second thing, and another thing is the story drift and story displacement. We have to check the story drift for both earthquake and wind loading. According for the earthquake, we have the story drift limit according to in the code, but for the wind, we have to check according to the cladding facade designer allowable drift. If the drifts are not within the limit, we have to revise our spectral system to maintain the drift within the limit. Same thing, we have to check the storage displacement. For the storage displacement, especially for the wing, we have the limit of h over 450, h over 500. It depends on the judgment of the designer. We should check those things first. And then we have to do the detailed design according to the code. For the preliminary design, using design basis level, we normally use the response spectrum analysis. We do not use we do not perform the nonlinear analysis. We use the site-specific elastic response spectrum, and then we design the building according to the code. Then we check we design the structural components according to the by using appropriate factors. For the response spectrum analysis, we have to scale down the base shear of the DBE level earthquake, because we do not want we allow yielding in DBE level earthquake. After doing the detailed design, we check the service level evaluation of the building. Normally in the code-based design procedure, if we design according to the code using 475 year return period earthquake, the building will, the code assumes that the building will respond, remain elastic and serviceable at 43-year return period earthquake for the which we call service level, and also it will not collapse for the very strong earthquake. We call it maximum considered earthquake with a return period of 2,475 years. So to get serviceable under the frequent earthquake, we use the service level response spectrum to check the building. So for the service level earthquake, we want the building to remain elastic. We do not scale down the base shear for the service level response spectrum analysis. We just do the elastic analysis using service level response spectrum. So the scale factor will be 9.81 for the service level analysis for the response spectrum. Then we check the story drift, coupling beam, and shear wall demand capacity ratios. For if we have the frame, we have to check the girder. If we have the girders, we have to check the girders as well. So in the performance-based design guidelines, we have the separate limits for the service level and MCE level. For service level, story drift is 0.5%, and all the members should remain elastic. And then we continue to check the collapse prevention performance level. In that level, we are going to check the collapse level, so the building will be highly nonlinear. So we use nonlinear response time history analysis. If we use the uniform hazard response spectrum, we have to use the 7 pairs of site-specific ground motion, which are matching with the MCE level response spectrum. And then we scale, and then we average the results of that 7 ground motions for the design check. Then we modified the preliminary design according to the requirement of the collapse prevention level check. In the collapse prevention check, we check the coupling beams, core wall, flexural response. For the nonlinear response, we check the deformation of those members, whether they are within the allowable limits or not. But for the brittle control action like the shear in the basement wall, diaphragms, columns, foundations, if we want to keep elastic, so we check their strength capacity of those members with the demand. So that DC ratios should be less than 1. Normally for the new buildings, we allow yielding in the coupling beams, shear wall flexure, and the girder flexure. But we do not want to, we do not allow the flexure yielding in the columns. This is the example building that I am going to present. It is a 30-story residential building. The total height is 92.8 meter, and the structural system is reinforced concrete ductile core wall, and we used a post-tension slab, and the gravity and surrounded by the gravity load resisting columns. This is the typical framing plan of the building. This one is the core wall configuration of the building. We have two types of link beams. In the middle, we have the long link beams, slender link beams, and at the boundary, we have the short link beams. These dark areas are the confinement zone of the shear walls, and which are not with a light gray areas are the no confinement zone. These are the member sizes. I use the one column size for the entire building, and same shear wall thickness. One type of link beam with conventional reinforcement, which L by D ratio is more than 4. I use 500-700 size, and for the same size for the link beam for conventional and diagonal reinforcement. And normal gravity load beams, I use 300-700 millimeter, and PT slab thickness is 25 millimeter. These are the material properties of the members that I use. In performance-based design, if we do the preliminary design, we normally use the nominal strength of the materials. That one we always use in the code-based design. But if we do the PVD for the service level and the collapse prevention level evaluation, we have to use the expected material properties. For expected material properties, if you have the real test results of the material, you can use directly. But if you do not have the actual test results, you can estimate the expected strength by multiplying with the factors showing in the guidelines. In TBI guidelines, to estimate the expected strength of concrete, we have to multiply with 1.3. To estimate the yield strength of the reinforcement, we multiply with 1.17. So we calculate the expected strength according to the guideline procedures. And then this is the loading criteria. Gravity loading, we consider all self-weight of structural members, and superimposed dead load, which consider the partition walls, floor finishings, and other utilities attached to the floor. We consider 3.5 kilonewton per meter square. Live load, residential area, 1.92 kilonewton per meter square. And we consider the dead load plus 25% of the live load as a mass source. This is the uniform hazard response spectra coming from the site-specific hazard assessment. The lowest one is the service level response spectrum. The red one is the design basis level response spectrum, and the blue one is the maximum considered earthquake level response spectrum. In service level response spectrum analysis, we have to take care about the damping. Because in service level, the building is not yielding too much. It's not yielding at all. So the damping will not be so high. We have to use 2.5 damping in the service level response spectrum analysis. For DVE and MCE level such response spectrum, we generate for 5% damping. In this example, I will not explain the service level evaluation because it is simple. Just run the response spectrum analysis using 9.81 scale factor instead of scaling down the base shear. So I will continue the collapse prevention nonlinear analysis. From MCE level response spectrum, we have to select the ground motions to mesh with that response spectrum. Normally, if you hire a geotechnical consultant to generate the site-specific, to do the site-specific hazard assessment, he will generate the response spectrum for 3 levels of earthquake, and then he will provide you the 7 sets of ground motions. In one set of ground motion, there are 2 records: false parallel and false normal records. In this example, I will show the results of only 1 ground motion. Normally, you have to run at least 7 ground motion and then average the results to check the design. This is the performance evaluation criteria of that building. We are going to check 2 levels of earthquake, frequent earthquake and MCE level earthquake. For the performance objective, service level, we want to remain the structure elastic, and collapse prevention, we allow the damage but it should not collapse. This is the acceptance criteria for the service level earthquake. The interstory drift should not be more than 0.5%, and the story displacement, this is the top story displacement, should be less than h/200. And all the members should remain elastic. When we check the demand to capacity ratio of the service level evaluation, the guideline allows until 1.5, not 1. So if the DC ratio is 1.2, we still allow. But we have to check the capacity using the nominal strength and then multiply with the code specified reduction factor. In the analysis, we use the expected material properties with 1.3 times FC, prime C, and the 1.17 Fy. But when we calculate the strength of the members, we have to use the nominal strength, and then we have to reduce the strength according to the code specified reduction factor. For example, for shear, phi equal to 0.75, so we have to use that phi factor to calculate the strength. And this is the acceptance criteria for MCE level. For MCE level, we have to check 2 types of drifts. One is peak transient drift. The second one is the residual drift. For the peak transient drift, the mean value of the story drift should not be more than 3%. But maximum drift from that 7 sets of ground motion should not exceed 4.5%. So we have to check both mean and maximum value of the analysis results. Then we have to check the residual drift. Residual drift means after the earthquake, the building is yielding a lot and it might not go back to the original position. It might be left in sway position. So if the building is swaying a lot after the earthquake, it is very dangerous to demolish the building. So the guideline limits the residual drift. So that drift we have to check at the end of the time history analysis. The mean value of that drift should not be more than 1 second and maximum drift should not be more than 1.5 seconds. This residual drift limit does not exist in the old guidelines. It starts added in the year 2010 document. And for the MCE level, we do not allow the column yielding, so column PMM ratios should be less than 1. Link beam rotation. We allow link beam to be yielded. In the link beam, we have two types of link beam with the diagonal reinforcement and conventional reinforcement. For diagonal reinforcement, the rotation limit is 0.03 radian, and conventional reinforcement, the rotation limit is 0.025 radian. For the shear wall flexural behavior, we check the shear wall axial strain in two ways. One is the rebar strain and second one is the concrete strain. For the rebar strain in tension, we limit 0.05, and in compression, we limit 0.02. For the concrete strain, compression strain, this is the formula to determine the limit, that we normally use 0.004. We neglect the second term to be conservative. It depends on the rebar ratio of the shear wall. And if we check the brittle action for this, these limits are for the ductile actions. If we check for the brittle actions, which is called force control action, we have to check, we have to increase the force, the average force by 1.5 times for the members if they are not limited by the well-defined yield mechanism. For example, for the girders, we can estimate the yielding location of the girders. Due to the lateral load, the girder will yield at the ends of the girder will yield at the end. So we can estimate the proper yielding as mechanism, and then we can do the capacity-based design clearly. But for the shear wall, it is very difficult to estimate the yielding mechanism. Shear wall will yield at the base, but it might also yield sometimes at the mid-height of the wall. So for the shear wall, we normally multiply with 1.5 times the mean value of the 7 ground motions when we check the shear wall base shear, and then we check the design. But if we have the well-defined yielding mechanism, example the flexural yielding in the girders, we just multiply the mean with 1.3 times and the standard deviation, but not less than 1.2 times the mean. To check the shear, to check the strength capacity of the brittle behavior, we can use the expected material strength, but we still need to use the strength reduction factor. So it is different from the service level evaluation. When we do the finite element model for the nonlinear service level and MCE level evaluation, we have to use the reduce the stiffness of the members. For the girders, we reduce 50%. So we have to, in sub model, we have to reduce M3 stiffness modifier to 0.5. And for the columns, also same thing, we reduce to 0.5. But for the columns, we have M2 and M3 components, so we have to reduce both directions. And for the shear walls, for the flexure, we have to reduce to 75%. So we have to reduce 0.75. But for the shear walls, we have to reduce to the F22 component only. We should not reduce M11, M22 stiffness of the shell element.